Good afternoon, everyone. On behalf of IIF Chennai Chapter, we welcome you all. This is Mr.Kumar, IIF Chennai Chapter Treasurer. Unfortunately, our chairman and treasurer, both secretary, are preoccupied with some programs. They are not able to join. And myself and our vice chairman, Mr. Raman sir, would be hosting this program. Is the voices clear for everyone?
Clear, sir.
I think you can use your chat and then give your comment so that we are aware that you are able to listen our voice. Good afternoon, sir. I would now request Mr. Raman sir, our vice chairman, to give a formal welcome note.
Yeah. Thank you, Sandil. I'm audible?
Yeah, you are relevant, sir.
Okay. Welcome, Mr. Kumar Kislay. Good afternoon.
Good afternoon, sir. Thank you.
Yeah. So, on behalf of IIF Chennai Chapter, I welcome Mr. Kumar Kislay and fellow Foundrymen for this wonderful presentation to be made by Mr. Kumar. Inoculation, as a process, we all know what need to be done and what will be the consequence on products. The fundamentals and the process requirements we all know very well. But the history, the evolution, and the current trends in with the explanation on case studies, those things will definitely enrich our knowledge so that our product requirements can be fine-tuned further. Ultimately, the customer will be getting satisfied. That is the prime requirement. So in that context, Mr. Kumar Kislay is going to give us wonderful presentation on these three topics, and he is head of research and innovation of Elkem Private Limited, South Asia. So I request all fellow Foundrymen to attend this program fully, and you can raise your doubts at the end of the program to Mr. Kumar so that our knowledge can be enriched further. So with that note, I request Sandil to introduce the speaker to the forum. Thank you.
Thank you, sir. Thanks for welcome speech. Good afternoon once again, fellow Foundrymen. It's great pleasure and honor for me to introduce today's speaker, Mr. Kumar Kislay. Actually, he is IIT Varanasi Metallurgy alumni and having more than 10 years of experience in the field of metal treatment and foundry metallurgy. Currently, he is working with Elkem South Asia Private Limited as Head Research and Innovation. And he has special interest in the field of metal solidification, thermal analysis, and metal treatment. In fact, he has published several research papers and conducted many seminars and webinars in this topic. He brings rich knowledge of inoculation and nodalizer for this session. I hope one of us will get benefit out of this session. I would request everyone to give an active participation, and you may keep yourself mute, and maybe end of the session, whenever you have queries, you can raise queries through voice chat or the chat. Mr. Kumar Kislay, forum is for yours. Please take over.
Thank you, sir. Thank you, sir. So what I would do is I would share my screen.
Yeah, that's better.
And then I request that if someone has a query or needs to ask something or get some clarification, we can either take it at the end of the session, or there is the chat box. We can also, write our queries on the chat box so that it can be taken up at the end for the discussion. Yeah. I hope the screen is visible to you.
Yes, sir, it is visible.
Great. So once again, good afternoon. It's really nice to be present amongst such esteemed audience. Though it's still online. We, with the onset of COVID and now that it is going towards the end, I believe we'll have more of physical meetings and interactions. But for now, we are connected online, and we'll try to make this session as interactive as possible. So the topic today is inoculation of cast iron, a brief discussion on the history, how it has evolved over time. Inoculation is not a very new concept. It has been there for many years, but it has not been the same all these years. So how it has evolved, and then what are the current trends? How do we look at it today? And how does inoculation help us foundrymen produce good castings? So before starting the session, I would uh, like to express my gratitude on behalf of Elkem, in fact, to the IIF Chennai chapter to give us this opportunity to be amongst such esteemed gathering and uh, give this opportunity for us to share the know-how and also learn something while we discuss the content. It's always a pleasure collaborating with such esteemed organization, and it's kind of a win-win for all of us where we share and learn and grow with time. Yeah. So thank you for that. To start the session, I have a few topics which I would love to you know uh, speak about or talk upon, starting with the current state, then with the evolution and history, uh, a bit of a detail on what does the inoculant do, what are the different inoculant elements, what is fading. We all quite often encounter or at least worry about the fade. So that how do you understand that the inoculant is effective? What does indicate that whether you have a good inoculant or a bad inoculant, or you need a better inoculant for the casting? And then how does Elkem work in all this with inoculation and metal treatment as a complete process to make the foundries better in the process? So the first, to start with, I mean, we have been talking, we will be talking about history, we'll be talking about evolution, and I'm sure that we have many senior foundrymen in the audience today, who have seen the growth and development of the foundry industry over the last few years. And I would like to emphasize on the few of the points. Like for example, we have seen the casting buyers having a much increase in the demand for the mechanical properties like the strength of the casting, the elongation, the ductility of the casting, especially for the SG iron, the impact properties when we talk about low temperature impact properties of in such applications, the impact strength of the casting, surface finish, of course, the surface finish of the casting, the machinability, and then after machining, how is the finish of the casting. Then we also are seeing nowadays unique grades coming into the market. I mean, I mean, if I talk about 10 years back, 15 years back, we had a much limited number of gray iron and ductile iron grades. But we have seen a lot of development in the last decade or so with so many, solution strengthened ferritic, and then silicon moly grades, and then some compacted graphite, and then CG, CMO, and like so many grades with improved strength as well as improved ductility. So that has come into the picture, which is kind of a challenge for us as a foundryman. And then how we, in terms of control in chemical composition, control on the metal treatment, control on the entire process of a foundry, try and achieve the properties which is desired to our uh, customers. Then, of course, the economics of the business comes into the picture, which means that we have to have a much tighter process control. We want to have minimum rejections. We want, yeah. So we see improvement in the process control. That is need for a tighter specification, better control, more consistency, repeatability of the castings that we manufacture and produce, and definitely that is where the better precision of our process comes into the picture. We talk about the foundry industry, we talk about emissions. So definitely we have to have a process where our entire foundry is more environmentally friendly today. The controls on emission, the controls on smoke, especially I'm talking about this when it comes to metal treatment, the ferrosilicon magnesium reactions that we see, and the kind of reaction violence and the smoke and the heat emissions that we see. So that is something that we need to control in future. Even today, we have the government norms which are which want the foundries to be more environmentally friendly and have minimum footprints. So that is something that we have to achieve. Of course, improved quality with consistency. Machinability, I mean, machining is a cost. So improving on the machinability of a casting definitely helps us, to be more competitive in the current market. And at the end of it, I mean, not the least, but definitely one of the most important points to reduce the cost of production. Uh, we are all foundrymen here. We know the prices are not going that up when it comes to the price of the casting, but the raw materials have been very dynamic. The prices have been very fluctuating. So we do want to reduce on the production cost to be more, competitive, effective, and productive in our business. So that has been the current state of the industry, and that is how these are the challenges. You can call it as the demand. You can call it as a challenge, or you can call it as the opportunity for us, because if we are able to achieve this, we will be uh, always the first choice for the casting buyer. So now, how do we reach this state, and how do we achieve this state? So I'm not going to look into the entirety of it, because then for that the session would be a bit short. But I would want to uh, talk about few of those things. So to start with, today the main topic is inoculation. So what is inoculation? We have been through the COVID in the last 2.5 years, and we have all been vaccinated. I hope we have all been vaccinated. Now is the time for the booster doses. So what does inoculation actually mean? I mean, if you go by the literal meaning of it, if you go by the actual word meaning of the word inoculation, it is basically vaccination. It is basically injection, a shot, something which is a external foreign particle which gets introduced into your system, which gets introduced into the liquid metal to improve the quality or the properties or the entire behavior of the metal. So that is what inoculation is. That is what the inoculant does. It is basically a foreign particle introduced into the system. Yeah. So we can correlate it with whatever we want. It can be called as a vaccine. It can be called as a booster dose or something which helps improve. It's quite similar to what we do when we get vaccinated. It helps our body become better or more effective towards the external forces or the external deleterious factors. So that's what the inoculant does to a metal or to a casting eventually. So now a basic or a short uh, trip down the history of inoculation. So it's not new, in the early 1900s. So that's about 110 years, 120 years before today. Uh, the casting was there, the metal was there, molds were there, and solidification was happening. So it's not that if you don't have an inoculant, you don't get a casting. You still get them, but of course it will not be the same in terms of quality. But what was happening in 1900s or so, we had the liquid metal which had some inherent hereditary particles within the metal, which was giving it the inoculating effect, which was giving it the site for the growth, for the solidification, for the phase change. So what was it? Most of it was the graphite. Graphite still today is considered as one of the very strong graphitizers. I mean, it gives you a lot of carbons conversion to graphite, which eventually becomes flakes or nodules or whatever. So graphite, the charged material, use of pig iron, use of use of charged metals which are rich in nucleating potential, and of course the history of the melt. I mean, the heat, the temperature, the time, etc. So that was the core essence of inoculation as a concept back in 1900s. Things changed a bit in 1920s or so, when we moved about 15 20 years, probably coinciding with the First World War, when we wanted when the industry wanted the metal casting pieces to be more efficient, more strong, better in strength, better in soundness. And that is when deoxidation as a concept was brought into the cast iron industry. And the major elements which were used as deoxidizers was aluminum, titanium, zirconium, and vanadium. So these were the main elements. Some of these elements still are used till today. So it has been 100 years since we actually started or discovered the use of these elements for the inoculation, and some of it is still there today in the inoculating concept. About 10-15 years back in 1930s, we had calcium silicide as the additive into the ladle. So the concept of adding something to the ladle more as a post treatment, not in the furnace, was done for the first time around 1930s. And the first material which was used as a ladle addition with the aim to modify or improve the quality of the metal was calcium silicide, which was done around 1930s. So after 1930s, once the liquid metal was, I mean, the concept of treating the liquid metal with some additives after the furnace came into the picture, there was basically a, a series of inventions which brought about many of the inoculating elements. Some of it, in fact, most of it, we see even today. So 1940s was the beginning. 1940s was the beginning, especially in 1942 to be precise. We saw the first zirconium and manganese based inoculant come into the picture. So I believe we definitely would be having some of the members today in the audience who have been using SMZ inoculant. That's a silicon manganese zirconium inoculant from Elkem, or maybe it can be a similar composition of of a inoculant from a different supplier. Because zirconium manganese is a very common inoculant even today. That was the first proper silicon based inoculant which had come into the picture in 1942. Barium calcium came much later. I mean, that's contrary to the not common understanding that we have, that barium calcium must be the first and must be the most common and original inoculant. But no, it came much later, maybe in around 1956. And 10 years later, we had the strontium inoculant, the supersede or any other strontium inoculant that we have for gray iron today. I would say that strontium inoculants, especially supersede grade of inoculants, are probably the best inoculants that we have even today for gray cast irons. There was a short period of time when magnesium was also introduced into the system as a inoculant. It had a, I mean, the role of magnesium was quite contrary to that of a calcium barium, because if I give you a basic a brief history on that, when magnesium was introduced as a inoculant, it was not added to give you graphitization effect. Magnesium was actually added to control the graphitization effect. So there was a team of scientists who were working in one foundry in Italy who was working on this, controlling the microstructure, and that is where magnesium was introduced on purpose to see if it can control the growth of graphite. Because we all know magnesium is a carbide promoter. Magnesium is something which negatively affects graphitization. So there was a small addition of magnesium added to the inoculant to have a better control on the graphite structure. A combination of strontium and zirconium in 87, a combination of barium and zirconium in 88, and then sometime in the 1980s itself, rare earths were introduced as the inoculating elements. Rare earths with bismuth came much later, not for a long period of time. Bismuth could never gain the popularity as an inoculant, but yes, it did come into existence sometime in 1980s. Towards the end of the century, 1998-99 was the first origin of sulfur and oxygen coated inoculants. So this was kind of, I mean, we till the time before sulfur and oxygen was added to the inoculants were supposed to react with the sulfur and the oxygen present in the base metal and then give the inoculating effect. But then one of the scientists came up with a origin of sulfur and oxygen coated inoculants. Quite proud to say he was from Elkem, who was the person who invented this sulfur and oxygen coated rare earth based inoculant, which was bringing its own sulfur, its own oxygen into the system, and thereby the dependence on the nucleating potential of the base iron came a bit less. So this again became, and even today it is one of the most potent inoculants for ductile iron. The combination of strontium, zirconium, and aluminum, that these are again now these are the main families of inoculants. And then we had many different derivatives, many different subsidiaries of each of these families, which with a lower or a higher percentage of a particular inoculating element, and that has been going on since the last 70-80 years or so. Even today we have foundries. I'm sure we have many inoculant manufacturers today, including Elkem and the others, who would be working on different combinations or different compositions of these inoculating elements to give the user the best and the most suited inoculant possible. So this was basically the origin and the growth and the evolution of inoculation over the last 120 years also. Where we are today, I'll see and I'll speak more about it in the later slides. But before I do that, let me give a short, a short introduction on what does the inoculant do. So what is an inoculant? Inoculant is basically an external additive, a additive which is added to the metal, and it can have once it is added to the metal, the additions can be in the ladle, the additions can be in the treatment ladle, pouring ladle, it can be in the metal stream right into the mold. So there can be different stages at which inoculant can be added. And what does it do? It creates those microparticles, it creates those small microparticles, basically the nucleating sites on which the graphite precipitates or the growth happens. So what are these microparticles? These microparticles can be the sulfides, oxides, nitrides, even carbides in some cases, which then act as a friendly site on which the growth would happen. So they act on the nucleation and the growth of the graphite. So what does the inoculant basically do? You have about 3.5% of carbon. About 2% of that carbon goes into the solution as the uh, solid solubility of carbon into iron, and then the balance 1.5% or 1.2% of whatever iron carbon is left, that has to precipitate out as graphite. That is what we want as a foundry. And if we do not make it precipitate as graphite, it would combine to form iron carbide. So what do we want to do? We want to introduce sites, nucleating sites, favorable conditions where this carbon would precipitate out in the form of graphite. Then whether it takes the shape of a flake or that of a nodule would be depending upon whether you introduce magnesium into the system or not. So thus, it acts as a nucleating site, it promotes the growth of graphite, and also ensures that because we have a control on the amount of sites, we are able to control the morphology of the graphite. How? I'll speak about it later. So what happens when you are able to ensure that graphite precipitates? This graphite would have a direct influence on the mechanical and the thermal properties of the casting. So whatever casting is manufactured. Yeah. Okay. So whatever casting is being manufactured.
Excuse me. We are getting some noise. Please put it mute, please.
Yeah. So what does this graphite do? This graphite directly influences the. I guess we also have an option to mute someone if you want.
Dinesh, please check it at your end. I'm also seeing. Please go ahead.
Yeah. Yeah. So what does this graphite do? Coming back to the topic again, it directly influences the mechanical and the thermal properties of the casting. So make sure that your casting has the desirable mechanical strength and desirable thermal properties, which is needed for the end application of it. Definitely, when you have a good inoculation and when you have a good graphitization, it also eliminates defects in the casting. Defects, for example, microporosities. Defects, for example, poor machinability. Defects, for example, improper mechanical properties, non-homogeneous mechanical properties. So all such defects, in fact, in some cases, some of the inoculants, even the gas defects can be controlled to a greater extent by having a better inoculation into the system. So to eliminate defect of castings, definitely inoculation does help, or it is a friend to us when we are producing castings. And finally, influences the customer processes. So there are inoculants which modifies the slag generation behavior, or it controls the slag generation, or at least creates has an influence on the amount of slag, the type of slag, and the quality of slag that is getting generated. So that way, it does influence the customer processes in a lot of cases. How does it do that? I mean, how does the inoculant do all this? So basically inoculant is a ferrosilicon alloy with some additives into it. The additives are the inoculating elements, which I had mentioned a few slides back, can be barium, calcium, strontium, zirconium, manganese, rare earths, bismuth, etc. What do these elements do? So these elements are chosen. I mean, the question can be, why only these elements and why not the rest of the elements which we have on the periodic table? So these elements have a very strong affinity towards oxygen and sulfur. So when they have a strong affinity towards oxygen and sulfur, they combine with the oxygen present in the system. They combine with the sulfur present in the system, and they also make sure that after combination with the oxygen and the sulfur, they create those inclusions, they create those small substrates on which the graphite would eventually precipitate. Now, why is it only ferrosilicon based? So that can be another question. Why can't we add pure strontium? Why can't we add pure barium or pure calcium into the system? So why a silicon based one? Why a ferrosilicon based inoculant? So this silicon which comes with your inoculant, which can be in the range of 50 to 75%, this inoculant, this silicon coming in with your inoculant creates a small zone which is rich in silicon. And this rich in silicon zone, I mean, I'm talking about very micro level solidification here. So there can be a very small, particle, a very small site within your metal, which will be very rich in silicon. And because it is rich in silicon, it gives you the constitutional undercooling. And when it gives you the constitutional undercooling, it allows for the carbon to precipitate out. It reduces the total percent of carbon that can be held by the iron, and thereby make sure that the total amount of carbon which cannot be held back by the iron comes out or precipitates out as graphite. So basically, this silicon reduces the solubility of carbon in your iron and makes sure that the carbon comes out. Now, when the carbon comes out, it needs to have a favorable environment or a favorable situation for it to precipitate as graphite. And that is where the inoculating element comes into the picture. That is barium, calcium, strontium, zirconium, etc. So silicon ensures that the carbon does not go into the system, it comes out. And the inoculating element ensures that this carbon which is coming out precipitates as graphite and does not again combine with the iron to form iron carbide. So it's a combination of role between iron, silicon, basically Fe, and the inoculating element that we introduce along with this ferrosilicon as the carrier. So that is how the inoculant works. And each of these inoculating element, like I speak about it in the slides later, has a specific role to play, has a specific characteristic, which would be the deciding factor for us as foundrymen on which inoculant to use for which particular casting and which particular condition. So I told you about how the ferrosilicon and how the inoculating element works. So like I mentioned, solidification would happen inside a casting, inside a mold. When you pour a liquid metal, the solidification would happen even if we do not add inoculant. So it's not that if you don't add an inoculant, the solidification would not take place. Why? Because your metal will have some inherent nucleating potential, will have some inherent impurities which would act as the site for growth. So there will be solidification. But then why to inoculate? Why do we want the inoculant to come into the picture? Why are we adding the 0.1%, 0.2%, 0.3%, 0.4%, or whatever is the addition rate of inoculant into our metal? Very simply, it can be explained here. I would use the pointer. Yeah. So it is explained very simply here in these two diagrams. If you look at the photograph on the left, it's a gray iron. I mean, you can see it from the microstructure which is shown below. It's a gray iron casting where you have a core, the core which is combined of strontium oxide, aluminum oxide, and then you have the manganese sulfide shell on the outside, and it is hexagonal in shape. If you look at it, it has 6 sides, so it's basically a hexagonal in shape. And this is the location, this is the site on which the carbon which was being thrown out from the iron matrix would precipitate as a graphite. If you do not have the strontium, if you do not have the aluminum, and if you're not able to combine with the oxygen, you will have a surface which will be triangular. It will not be a hexagonal. And on this type of a surface, the graphite precipitation will not be the same as what you have on a hexagonal core. Now, why do you not have a graphite on a triangle? Why do you have it on a hexagon? I will give you the answer to that in the next slide. Of course, when you have this kind of a surface, when you have this kind of a structure, the kind of microstructure that you get would be more of a type A, random distribution, a much better graphite flake distribution, much better control on the flake thickness, the length of the flake, and a random distribution would make sure that your casting achieves all the mechanical properties and the thermal properties that it is supposed to achieve. Plus, if you also look at the wedge, which is corresponding to this kind of a microstructure, you have minimum carbide, so minimum chill. On the other hand, if you have this kind of a microstructure, if you have this kind of a solidification taking place, the microstructure would be more of undercooled graphite, that will be type D and a combination of type D and E. What does this do? This causes a poor machinability. This causes poor mechanical properties, poor thermal properties, and also it makes the casting behave in such a manner that it has a higher tendency for carbide, because you're not allowing the carbon to completely precipitate out as graphite. So when the carbon does not come out as graphite, it combines with the iron again to form iron carbides. Like I said, solidification would happen even without inoculation. But why does or how does an inoculant help? A good inoculant, and now I'm talking about ductile iron here. We spoke about gray iron before. In case of a ductile iron, a good inoculant will form on the hexagon oxides of inoculant and oxides of aluminum and silicon, which is present in your system. This will be around the core. The core will be made up of magnesium. Of course, you don't have the manganese sulfide acting into the, in case of SG iron, you have more of magnesium sulfides and calcium sulfides, which forms the core. And then you have the shell, which is made up of oxides of silicon and magnesium. So this is without inoculant. In this, you do not have a favorable site on which the graphite would precipitate, even though you have a core which is formed. But in this case, when you add an inoculant to it, which can be any of the inoculating elements, you are creating a site, you are creating a situation where the precipitation of graphite will be in a much more favorable manner, in a much more friendly manner. Now, the second question. Now, why do you need it to be a hexagon? And we are talking about magnesium. We have been speaking about affinity of sulfur and oxygen. We have been speaking about how the inoculating elements, because of its affinity towards sulfur and oxygen, becomes a inoculant. Then there should be a question that we all know magnesium also has a very strong affinity towards sulfur and oxygen. So when magnesium has affinity for sulfur and oxygen, why it is not an inoculant? Why do we not see magnesium acting as an inoculating element? And why do calcium, barium, strontiums, etc. are acting as an inoculating element? A basic explanation to that is, when you have the silicates of magnesium, the silicates of magnesium are not hexagonal in shape. Now this is pure chemistry. I'm taking you back to your class 10th, 11th, 12th or so. I don't remember when did I study this. But yeah, magnesium silicates are not hexagonal in shape. They are orthorhombic. While on the other hand, silicates of calcium, strontiums, and bariums and zirconium are hexagonal in shape. So how does it affect graphitization? Graphite has a hexagonal crystal structure. So when graphite, which is a hexagon, and the silicates of calcium, strontium, barium, which are also hexagon, combined together, it ensures that the graphite would precipitate on this type of a structure and will find it very difficult to precipitate on a orthorhombic kind of a structure. So that is the reason why you have, despite having a strong affinity for sulfur and oxygen, magnesium is not a inoculating element, but calcium, strontiums, and bariums are inoculating elements. How does the inoculant look? I mean, what is the inoculant? How does it look at under the microscope? And we only talk about the graphite structures. We only talk about the flakes and the nodules. But how does the inoculant actually see? I mean, I showed you the schematics of it, but now we are seeing the actual magnification, higher magnification images of the actual core and the actual graphite precipitating out. So these are the microstructures. I mean, you can see it. This photograph was taken in 1993 by Torbjörn Skeg, and he still works for us. So he's one of the Elkem stalwarts, if you want to call him. So he was the guy who in 1993, in fact, tried to look under the microscope, transmission electron microscope, and found the actual core of a graphite, found the actual core of solidification. And then we were also able to capture the different elements and how do they look under the microscope. So you see the different elements which promote or support graphitization in the casting. So this inoculation basically coats the microparticle, the core, which are naturally generated, reduces the undercooling, and thereby promotes the nucleation or the graphite precipitation. I spoke about few elements. I spoke about maybe 2 or 3, but now we will look at the different elements and how do you choose or select between inoculants. We have calcium inoculants, we have barium inoculants, we have strontium inoculants, aluminum inoculants, etc. Which to choose, when to choose, and why to choose. Calcium, one of the most common and readily available inoculants in the casting. Sometimes we also get ourselves confused by considering ferrosilicon as the inoculant. Ferrosilicon is not an inoculant. Why it behaves as an inoculant is only because it has got some calcium in it. The ferrosilicon has, any ferrosilicon which we buy from the market would have about 0.1 to 0.4, 0.5% of calcium in it. And this calcium is actually what makes sure that our ferrosilicon also acts as an inoculant. It is an essential element. Most of the inoculants have calcium inherently in it, except maybe 1 or 2. It is a medium potent inoculant. It does not have a very strong potency. It has a much faster fading rate, so it fades pretty quickly. And if you're using a calcium inoculant, definitely you have to add a lot more of inoculant into the system. Second is barium. In most cases, in combination with calcium, this inoculant is there. It's quite a universal inoculant, means it can be used for both gray iron and ductile iron, and also in fact for the compacted graphite iron. So barium for that matter has a much wider application range compared to some of the other inoculants. Because it is barium and because the barium oxides that are formed has got a much higher fading time. So a barium inoculant has a very good fade resistance. So the foundries which are having a longer pouring time or a longer process time after addition of inoculant, barium is the way to go. It does, because barium has a strong affinity for oxygen, and usually the barium inoculants have got a much higher content of barium to the range of 2.5 to 3% or so. When added in excess, barium inoculants can give you slag defects. So the castings which have a design which are more prone to shrinkage, more prone to slag inclusion, barium is an inoculant which you should be a bit careful about when you're using it. Strontium is another superstar of an inoculant basically. So it's one of the best inoculants for grey cast iron. A very highly potent inoculant, has a very good ability to control carbides, thereby making it the first preferred inoculant, especially for the thin section castings. It also reduces the tendency for shrinkage, especially at the thick and thin intersections. You as a user might not have to add too much of a strontium inoculant. So that's one of the benefits. Another, because it has got a very strong potency, strontium additions, even at a rate of 0.1 or 0.15 or so, does give you a very good effect. There is a limitation to it. Strontium inoculant does not or cannot work effectively or in a very good manner if you have calcium present in it, in the system. So that is why most strontium producers do not add calcium to it. And this is one of the main reasons why strontium inoculant are not used in ductile irons. Because ductile iron treated with ferrosilicon magnesium would have some calcium inherent in it. And that is the reason why strontium does not behave in the manner which it should in case of SG iron. So a strontium inoculant is more commonly used in case of grey cast iron. Aluminium inoculants, again, are not very common inoculant, but we do have aluminium present in almost all the inoculants that are there available in the market. A small amount of aluminium does improve graphitization. We saw the aluminium oxide forming the core in the slides before. It improves the dissolution rate. In fact, aluminium inoculant finds its maximum application in heavy section ferritic ductile iron castings because it has got a very good tendency to promote ferrites. So most of the in-mold inoculation that you would see, the inserts and those blocks that we add into the heavy section castings, especially windmill castings or so, they are in most cases aluminum-based inoculants. The next one, that is zirconium. Zirconium-based inoculant in combination either with strontium, in combination either with barium, in combination with calcium, and sometimes even independently, has got a very balanced effect on the casting solidification. It can find application in both gray and ductile iron castings. It does refine the structure in a very good manner, and especially for the castings which has got heavy cores and which can potentially have nitrogen fissure defects also. Zirconium inoculants finds use over there because it controls the nitrogen fissure defect in the castings. In combination with strontium, zirconium inoculant also helps in controlling the length of graphite flakes in case of gray iron, and also the coarsening of graphite flakes. So foundries which are having type C graphite problems, apart from definitely controlling the carbon equivalent, a zirconium strontium inoculant, and foundries which are having thin and thick section castings producing gray iron castings which are both heavy as well as thin sections. Having a plain strontium inoculant may or may not be useful. There, a combination of zirconium and strontium does give a very good effect. One of the latest or modern inoculants has been the rare earth based inoculants. So rare earth basically means primarily means cerium and lanthanum. The rare earth elements find inoculants find application more into the ductile iron castings. It helps improve the nodule count substantially in case of ductile iron. It has got a very good tendency to control the carbides and shrinkage in the casting. Even if you have a pure magnesium treatment, even if you do not have a ferrosilicon magnesium treatment, many foundries use rare earth based inoculants to reduce the effect of subversive elements, the elements which otherwise would have caused poor nodularity, for example titanium. So to control the effect of those elements, rare earth based inoculant can be in use. But then again, people have to be a bit careful with the addition rate of these rare earth elements, because a higher addition rate can mean that you are introducing more cerium and lanthanum into the system, which would eventually mean that it can cause a tendency or a potency for chunky graphite in the system, in the castings. Manganese, another common element which has been there into the inoculating world for many years. It, in combination with zirconium, can give you a very potent zirconium manganese based inoculant, especially for the gray iron, where it works even at a slightly lesser content of sulfur. If for some reason the foundry is not able to maintain higher sulfur, a zirconium manganese kind of inoculant can give you a much better effect there. Then again, a low temperature casting, low temperature foundries where the metal temperature cannot go very high and they may face some problems of dissolution of inoculant. A manganese based inoculant helps you there because it reduces the melting point of the inoculant. So thereby it ensures that your inoculant dissolution improves even at a lower addition temperature. And definitely we all know manganese is a perlite promoting element. So a manganese based inoculant can assist, support, or promote growth of perlite into a perlitic grade of casting. And that is also one of the reasons why a manganese based inoculant finds its application more into gray iron compared to ductile iron. We spoke about the basic ones. Now I'll just talk to you about, I did say a few words about the sulfur and oxygen in the last slide. So what was happening in up to early 1990s was that we had the ferrosilicon alloy and we were adding all these inoculating elements into that ferrosilicon alloy. And then when this inoculant was added into the metal, added into the melt, this inoculant would combine with the sulfur and oxygen, which would be present in the iron melt, and thereby form those potent nucleating sites on which the graphite growth would happen. But in early 2000s or late 1990s, the concept of the inoculants bringing their own sulfur and oxygen came into the picture. So the concept was that we add sulfur and oxygen along with our basic inoculating elements into the system, which acts as a non-metallic inclusion. So it's basically a non-metallic inclusion which goes into the system. And because the sulfur and oxygen is there, it would combine with its own inoculating element to give you nucleating sites. And these nucleating sites, along with the already available nucleating sites in the iron, will give you a much better nucleation. And better nucleation means more nodule count. It means much better casting homogeneity. It means much better control on shrinkage, much better control on carbides. So sulfur and oxygen coated inoculants came into existence about 20 years back, and since then they have been the go-to inoculants for many foundries who have been struggling with a a inferior base metal. When I say inferior base metal, what do I mean here? Say we know pig iron can be a very good promoter of nucleating potential inside a base metal, but we also know that pig iron can bring with it many elements which we do not want them to be there in our iron, say for example titanium, phosphorus, sulfur, etc. So when you do not add pig irons, when the ductile iron manufacturers do not add pig iron, they inherently reduce the nucleating potential, because even when the pig iron was bringing the bad elements, it was also bringing in the nucleation. So the compromise was that we had to control the negative elements, and that is why we had to control the pig iron, but then we lost out on the nucleation. So how do you bring the nucleation back? One of the ways is to precondition, of course, but the other way of doing it is if you have an inoculant which brings its own nucleating potential with it, and thereby along with the nucleating sites, it also gives you some additional nucleating sites along with the ones that you already have. So this was the reason, this was the concept because of which the sulfur and oxygen coated inoculants came into the picture, and that was the origin of this new, flagship of an inoculant that we see in the market today. Inoculation is the addition of a ferrosilicon based product, but we also add ferrosilicon in our system. We also add, ferrosilicon more so to increase the silicon content in our system. But that silicon which comes in from your ferrosilicon addition stays in the system. But the inoculation, the effect of inoculation does not stay forever. So what do we say? What do we call this phenomena? We call this phenomena as fading. So the effect of any inoculant, I mean, whatever inoculant you add into the system, the effect is going to fade. It can have a different time. It can have a different effectiveness. It can have a different, end effect. But the inoculant will always fade. The fading of inoculation starts right after the addition of the inoculation. So there is a very small degree of fading which happens when you add the inoculant. But over time, the rate of fading increases substantially. There are definitely few of the inoculants, like I mentioned, barium, which does fade a bit slower than the other inoculants. And why does this fading happen? We'll see about it in the next slide. But what happens when your inoculant fades? When your inoculant fades, you have an increased undercooling. It means you have a poor graphitization. It means you also have a much higher tendency for carbides. It means that you have a reduction in the number of eutectic cells. You have a much lesser uniformity in the flake distribution in your gray iron. You have a much lower count of nodules in your ductile iron. And because you have a much lesser nodule count, your nodularity will also get affected. So at times we have seen the nodularity being poor in a casting, and we have tried to solve it by improving on the inoculation. And that has worked. So in nodularity as such is not only dependent on the ferrosilicon magnesium that you add, it also depends on the quality of inoculant that you add. And of course, if you are able to, and if you end up with all these problems, eventually the property of the casting is also going to get reduced. This graph on the right tells us that the fading of, the inclusion number, so basically the nucleating sites in case of addition of inoculant is the highest when it is added, and then this rate keeps coming down up to 10 minutes, and then it goes all the way up to 0. So to some extent, up to about 10 minutes, or to be more on the safer side, up to about 7 to 8 minutes, you get the sufficient desired number of inclusions or the nucleating sites for the graphite to happen. Anything beyond that, beyond about 10 or 12 minutes also, the inoculant is as good as not added. Why does this happen? Why does the inoculant fade? So when you add the inoculant, you actually create a lot of nucleating sites. You create a lot of locations on which the graphite would precipitate. But after time, for these nucleating sites, or these sites find it very difficult to hold on to its number or hold on to its size and shape, because they are very micro in terms of its size. So what do? They have an inherent tendency to try and combine with the next one. So the The two sites which are close to each other, they will try and combine to form a, a bigger site. And once it becomes bigger, it becomes more stable. It becomes more, safe. And this tendency keeps on happening with time. The concept is called ripening. Ostwald was the scientist and on who found this, and based on depend on and on his name, this effect is called Ostwald ripening effect, where these small nucleating sites basically ripen. They become bigger, and eventually, when they keep becoming bigger, the nucleating sites, the number of nucleating sites keeps coming down. And as the nucleating site keeps coming down, the inoculant effect keeps coming down, and that is what we call as fading of inoculant. What do we want to do? We want to make sure that our complete solidification and complete casting happen sometime here. Not the solidification, but at least the casting should happen sometime at across around this time, so that you have sufficient amount of nucleating sites for the graphite precipitation. But then how do you analyze if your inoculant is good? How do you analyze if your inoculant is working properly? You add it by looking at the chemical composition. Yes and a no. I mean, just having the silicon increment, I mean, you will not have increase of any other element basically. Maybe silicon, maybe about 60% of your inoculant addition will be silicon. So we'll have some increase in your silicon. But just having an increment in silicon does not assure or ensure that your inoculant is working. That is basically ensuring that your inoculant is added. So if you add the inoculant, you will have some silicon increase. But that is just a part confirmation that the inoculant has been added. A better way of doing it is to look at the microstructure. So when you look at the microstructure, you'll have a much better graphite precipitation. You'll have a much better carbon control. You'll have a much better uniformity in your structure. Even more potent and accurate way of looking at is the thermal parameters. So you look at the thermal analysis, you look at the thermal parameters, you look at the lower eutectic temperatures, you look at the solidus temperature, you look at the graphite precipitation behavior, you look at the angle towards the end of solidification to see if you have enough graphite precipitation. You look at the recalescence. So these parameters give you a very direct indication on the effect of nucleation. Further, if you're able to achieve a good microstructure, if you're able to achieve a good thermal parameter, definitely the mechanical properties are the next things which will give you an indication that your metal has been properly inoculated. When you have a good microstructure, when you have a good graphite precipitation, it means random graphite flakes of controlled length and thickness in case of gray iron, and a desired nodule count as per the section thickness in case of ductile iron. So when you are able to achieve these two, you will be able to also achieve a very good matrix, which can be purgatic in case of gray and ferritic or purgatic depending upon the grade that you are producing in case of SG. This combined together would ensure that you also have a very good machinability on your casting. Then when you are able to get the desired graphite precipitation, it would mean that you will have a much better control on your carbides and the chilling tendency in the casting. And when you're able to have a good thermal properties, a good mechanical property, a good microstructure, I'm pretty sure that we will also have a much better casting soundness. When I say casting soundness, I mean the casting which does not have any voids, does not have any porosities, does not have any shrinkage, something what you see here. So what is happening here? It's a very interesting typical photograph of a gray iron casting which has these dendrites. These dendrites are the austenite which is precipitating, and this is directional solidification which is happening because you do not have enough nucleating sites. When you do not have enough nucleating sites, the casting would still solidify, but then it would solidify in a direction. This is called directional solidification, and this particular branch structure is actually the dendrite. So this dendrite is formed, and this dendrite will make sure that you get more of a type D and E graphite precipitating on both sides of it. And if the inoculation is so poor that you actually even don't see the graphite precipitating out, what you will see are these voids. These voids are basically shrinkage cavities, and these dendrites have made sure that any possibility of feeding liquid metal into these last to solidify sections has not been possible, and that is why this kind of shrinkage was faced by the casting manufacturer or the casting producer. How do you control this? You control this by having a more uniform solidification, by creating more nucleating sites, by making sure that you have a very good inoculating effect into the system, and also by controlling the rate of solidification. And if you are not able to control the rate of solidification in the given time of solidification, you have to control the rate of graphitization. So you ensure enough graphites, you ensure that you do not have this directional solidification, you ensure that you have enough graphite precipitation, which would compensate for the volumetric shrinkage, and thereby you get a much better casting soundness and do not end up with something like this. Or something like this, where you see these carbides and where you see this not so good nodularity. But does a good inoculation ensure that you get a very good casting? Or does it alone ensure? Definitely it helps, but it is not just the metal treatment or the inoculant. This is more of a disclaimer from the inoculant manufacturer, that it is not just the inoculant which ensures that you get a very good casting. It's more towards the process stability. It's more towards the process conditions like the base iron, the treatment size, the treatment temperatures, the holding time, the design of the ladle, and eventually the treatment alloys that make sure that you get a much better process stability, you get a much better casting. And what do we have to do? We have to always make sure that we work from the bottom to the top. So unless we are taking care of these parameters, unless we are looking at these conditions, just relying upon and depending upon the treatment to take care of the the issues that we have in the system will not always give you the best results possible. So we have to work in this direction. We have to make sure that the rest of the system is good, and then definitely inoculant is a friend which would help us produce the good quality castings. Now I talk a bit about what does some of the new products, what does some of the new concepts, and how do they help us get the best of our inoculation, and also get us help us to improve and eventually achieve the best quality castings. Preconditioners. We spoke about the furnace. We spoke about the inherent base nucleating potential. We spoke about the quality of the base iron, and we also spoke about the limitations and the dynamics of raw materials that are there today. So the cost of it and the impact of it. So in some cases, we end up having a not so good base metal. It could be because of the raw materials, it could be because of the process, it could also be because of the limitations that a foundry has, and then it could also be because of the heavy critical requirement of the casting. So when the casting needs something extraordinary, maybe the inoculant alone may not be able to give you the desired effect. And in all these cases, we tend to introduce a preconditioner. A preconditioner is basically a furnace additive added in the range of maybe 0.1 or 0.2%. And what does it do? It ensures that it improves the quality of the base iron, makes it consistent, improves the morphology of graphite, negates the impact of tramp elements or trace elements, reduces the tendency for carbides and shrinkage, improves the mechanical properties, reduces the need for pig iron. We talked about pig iron bringing in unknowns into our system, and still we are dependent on it for a lot of nucleating benefits that it brings with it. But the need for pig iron can be reduced or may be needed to be reduced, and that is where preconditioning helps. It reduces the impact of superheating and holding time. This is what I'm talking about, the foundry conditions. It can have a layout, it can have a kind of a setup where you do need to hold the metal, or you do need to superheat the metal, and that is where reducing the impact of it can be done by addition of a preconditioner. It does eliminate issues which can arise due to other preconditioners like silicon carbides, rusted scrap, ferrosilicon, graphite, extra. So these additives also add or work as a preconditioner, but they bring their own set of problems with them. And when you add up silicon carbide, you end up with inclusions. When you add a rusted scrap, you do not know how much to add, or you may have to add a lot. When you add a ferrosilicon, you do not know how much of a calcium content it has. So that means we are not sure how effective it would be. There will be a limitation on the graphite that you are adding. So all these negative elements or the aspects can be controlled when you have a preconditioner, more like a pre-seed. Another way of doing it, I mean, I'm talking about these are basically additions to the inoculation. The other way of doing it is by having a very good treatment cover. So when you're producing ductile iron, we all know that we have punching scraps, or sometimes even turning borings or other such things which we add as a cover. The role of the cover in these cases is to delay the magnesium reaction. What do we want to achieve? We want to achieve that the magnesium reaction should happen when you have sufficient amount of metal in your ladle, so that you get a better recovery of magnesium. But that is not always possible with the covering scraps. That is not always possible with the turning and borings. Why? Because these covering scraps, these turning borings, one, they need a lot of heat for the melting, and two, they may bring with them their own set of unknown elements into the system. It can be oil, it can be rust, it can be lead if the scrap is coated or painted, it can be zinc. So there can be many more things which these covering scraps can bring with it. And when you have such kind of a covering scrap, your inoculation and even your ferrosilicon magnesium treatment will not be effective. So what do you do in that case? You add a known cover, a cover for which you always know that what is the chemical composition of it, and you do add less of it. How does it help you? It improves in the recovery of magnesium. It conditions the slag, so make sure that you have dry slag so it does not go in with your system, go into the system, into the molds. It increases the nucleating potential. Definitely, it improves in you getting a much stable process compared to unknown covering. It reduces the power cost and the cycle time. Of course, we can take it as a separate discussion. How does top seed help us achieve all this? It reduces the addition rate of ferrosilicon magnesium. It reduces the basics variation in the system. And like I mentioned, it eliminates the impact of unknown scrap. I mean, there are case studies where we have seen it, a use of top seed, reducing the addition rate of ferrosilicon magnesium, reducing the requirement of inoculants, and also reducing the tapping temperature and time. So basically the cycle time and power cost. And finally, I have been talking about it since the beginning, the ultraseed family, that is the sulfur and the oxygen coated inoculants. So a ferrosilicon based inoculant, like I have mentioned, does have active elements. But when these active elements are coated with sulfur and oxygen, it allows them to form its own inherent inclusions, which give you a much better graphitization and gives you a much better control on the carbides and microporosity. This type of inoculant, I will not speak again about it because I've already done, is more suitable for both thick and thick section ductile iron casting, and definitely finds its application more into ductile iron casting compared to the gray iron casting. So with this, I will give you a very small sort of teaser on how do you actually look at a defect, and how does the technology help us, identify or understand the defect better. So this is just the last part of the presentation. The casting, there is a casting which has got some defect, and this defect was sent for analysis. Of course, the foundry, when they look at the casting defect, the foundry did identify it as a slag inclusion. And we thought that let us look at the problem again and try and see what it actually is. So when we did look into the casting, and we did look into the casting using the SEM and the EDS that we have with us, we identified some silicon carbide inclusion. We identified some slag inclusion. So yes, the foundry was not completely wrong. They did have some slag, but it was not just slag. We identified some of the aluminum oxides, zirconium oxides, and silicon carbide inclusion. Where would this come from? Probably from a broken filter. That's possible. And the broken filter itself might have caused slag inclusion because it was not able to trap the slag in the root. And then, interestingly, we also found some resin and coal and coke inclusion inside the casting. So it was a combination of these 4 different inclusions which was giving them the casting defect. So do you think with this kind of a setup, just having a control on slag would have resolved the problem? No. So this is just to reinstate the fact that when we use technology, when we don't go just by our, the traditional or the original ways of looking into a defect, we will be able to do a much better root cause analysis and eventually get a much better solution to the problem. With this, I would love to thank all of you for your patience and listening to the talk. I believe the floor is now open. Thank you.
Thanks, Mr. Kumar Kislay. It's a very exhaustive presentation. I think
Thank you.
people who have been participated must have been benefited. I hope we can allow if the participants have any questions. I would like to ask them a few questions or put your questions in the chat box. You can unmute yourself and ask question.
Hello.
Good afternoon, sir.
Good afternoon, sir. Please introduce yourself, sir.
Sir, from calling from KP Foundry, Belgaum, sir.
Oh, very well. Thank you, sir. Tell me, sir.
Sir, we are finding C-type graphite in the heavy section of the gray irons. So, how to reduce that? Which is the best inoculant to use this?
Okay, so you're getting what I could understand is that you're having C-type graphite and you want to understand how to control it, right?
Sir, it is in the thicker
Yeah.
section, not in the thin section. It is in the thicker
Yeah.
section.
So yeah, so we'll have to.
And also, sir, we are finding some phosphide microstructure in that section.
So you're getting some phosphide eutectic in the system, in the similar structure.
Yes.
1 or 2%.
Yeah. Okay. Two ways to control it. I mean, because you have a heavy section, you have a much slower solidification rate. And because you have a much slower solidification rate, it means we are giving a lot of time for the casting, for the graphite to precipitate out. So on a flake or on a site where the graphite is precipitating, because the time is high, the solidification rate is slow, it means that a higher amount of graphite is precipitating and accumulating at a particular location or a particular site, and that is giving you a type C kind of a graphite structure. To control it, there can be two ways. I would not go the chill route. I don't want to do that. I don't want to suggest that as the first option. But before that, if you want to control type C graphite, one is to look at the chemical composition. So definitely, if you're not having any shrinkage problem as such, I would suggest to bring down the carbon equivalent up by a bit.
Okay.
Maybe to see if we can bring down the carbon equivalent by 0.1 or 0.15 or so. Reducing the carbon equivalent will reduce the amount of carbon present there for the precipitation. That's number one. But if you're facing shrinkage problem, and reduction in carbon is promoting shrinkage, which happens in many cases, the other way to do it is to improve the amount of graphite, to improve the number of graphite flakes. So when you improve the number of graphite flakes, you also ensure that your carbon gets distributed or your graphite gets distributed, thereby you don't get coarsening of graphite. That can be done by improving on the inoculating process. Either we can introduce a better inoculant, I mean a higher potent inoculant, or we can increase the addition rate of inoculant, or if these two are already there, maybe we have to introduce the preconditioning of the base metal to make sure that your system is more inoculant rich and more nucleating rich, so that you control your type C. Now the second question was about phosphide eutectic. Phosphide eutectic again forms when you have a higher percentage of phosphorus. So when you have a higher percentage of phosphorus and you allow it more time to precipitate, it will go into the grain boundaries to form the phosphide eutectic. The best way to do it is to control phosphorus. You will have to see where does the phosphorus come from, and then maybe try and control the amount of phosphorus that you have in the system.
How much can be aimed for that phosphorus?
So that depends on the casting that you're making. I would suggest anything between for gray iron anywhere between 0.03 to 0.6 should be okay.
Okay.
Beyond that, it can have a problem unless you are making wear resistant parts. So wear resistant parts in there, phosphide eutectic actually is advantageous because it gives you a much higher wear resistance. But if you're not producing those kind of castings, a top cap of 0.06 should help you solve the problem.
Right, sir.
Mr. Kumar, there is one more query in the chat box. I think Mr. Sandil Kumar, MD of Blue Moon Casting, has posted a chat. Up to what thickness or weight of the casting strontium inoculants could be used in the gray iron?
Okay, so See, so strontium inoculant, if you're using pure strontium inoculant, I mean just the strontium inoculant, I would suggest not go for a strontium inoculant if you're going more than 20-25 mm section in thickness. If you still have to, if you still have a casting which has a both thin and thick section, thin and thick section where the need for a strontium element is there, I would suggest to go for a inoculant which is more in combination with strontium and zirconium, which will help you get the carbide control, but at the same time also ensure that you do not have a very long or thick graphite flake. So more of a strontium plus zirconium inoculant can help you if you have a heavier section. I have seen foundries using strontium zirconium inoculants all the way to up to 35, 40, 45 mm section. So that should not be a problem.
Sanjil sir, hope it answers your query. And there is one more query. You can read it in the chat.
Yeah, I'll just read up. I'll read the mail. I mean, there is a question which talks about give me a good insight of Okay, that's a feedback. So the question is suggest how to maintain flake size 3 to 4 in cylinder blocks. Control on chemical composition, control on the carbon equivalent, and making sure that you use a strontium based inoculant in the cylinder blocks. Strontium zirconium inoculants in cylinder blocks is something that we have been recommending for many years now. So that can be a really good inoculant if you want to use it for the cylinder blocks, and that should help you get your graphite flakes in the range of 3 to 4 of a size. How can we promote graphitization if the solidification time more than 10 minutes? Particularly medium and huge weight casting solidification processes prolonged period, especially at hotspots and below the riser neck in ductile iron manufacturing. You have to, I mean, any of us have to inoculate as late as possible. So basically that is to control the inoculant fade, especially in case of a heavier section casting or in case of big castings. One way, a simpler way of doing it is to have a metal stream inoculation, the MSI 0.2 to 0.7, which goes directly into your mold. That can be a way of doing it. If you go even further, like say, I mean, we have seen castings being manufactured in the size of like say 5, 10, 20, 30, 40 tons. The better way to do that is to have a insert or a in mold inoculation to solve it. But if we are not going to do that, metal stream inoculant actually is something which helps us achieve it. How to avoid white patches in ductile iron? White patches are basically patches which are devoid of carbon, which are devoid of nuclei. And how do you do that? Is once you have a more homogeneous, better distribution of inoculation in the system and a more uniform solidification behavior, maybe that should help us resolve those problems. We have chunky graphite structure in thick section components. Please guide us how to eliminate it. Thick section casting chunky graphite. Please look at the residual cerium and residual lanthanum that you have in your material. Try and use low rare earth based ferrosilicon magnesium so that you are able to control the total cerium content. Make sure that your magnesium plus cerium plus lanthanum should not go beyond 0.05. That's a thumb rule. I'm not giving you a written statement, but we have to make sure that our magnesium and cerium should not go beyond 0.05 or 0.55, especially when we are making a heavy section casting, because more amount of cerium and magnesium in combination will give you chunky graphite. Definitely, we have to also look at carbon equivalent. You cannot have a lot of carbon coming into the system. You have explained about inoculation. Same, and can you please explain how preconditioner works? So what does a preconditioner basically do and how is it different from inoculant is? Preconditioning is basically done by the inoculating elements or by the elements basically, which combines with the oxygen to create more amount of oxygen and sulfur rich sites, and it has a much longer fade resistance. So a preconditioner, in case if you are using I would use the most common one, the zirconium and the aluminum based preconditioners. They have been known to give preconditioning effects all the way up to 8 to 10 hours. So a metal which has been preconditioned using a zirconium or aluminum product does have a much better nucleating potential even up to 8 to 10 hours after the addition. So that way, inoculation is something which has got a much quicker fading. But aluminum and a zirconium-based preconditioner, of course, it has got a much higher percentage of aluminum and zirconium, and that is why it is not used as an inoculant, but used as a preconditioner. Gives you nucleating sites, which stays rich in nucleation, which stays stable for a much longer time. How to increase the lower eutectic temperature in the furnace metal? To increase the lower eutectic temperature in the furnace metal, you have to have a very good nucleating potential in the metal. Lower eutectic temperature is basically the temperature at which your carbon precipitates out as graphite. You want this temperature to be as high as possible if you are producing castings, because otherwise, if this temperature goes too low, I mean, if the temperature, lower eutectic temperature goes very less, it can go up to the white zone, that is the white eutectic, and then you can have a much higher tendency for carbides, or if not carbides, at least for the undercooled graphite. What is the recommended minimum temperature? I mean, that depends from between casting to casting, but if you talk in general, your gray iron casting or a ductile iron casting, in fact, the gray iron casting should have a minimum lower eutectic temperature, the base metal, to the range of 1130 to 1135. In case of ductile iron, because you have a much higher carbon in your base metal, so your lower eutectic temperature will be in the range of 1140 or so. It should be. But then again, this is a recommendation, a general thumb rule. It will depend, and it should depend between casting to casting and foundry to foundry. Could you please state the relation between inoculation and hardness and machinability issue in gray iron thin walled casting? Yes, when you add an inoculant, you control carbides. When you control carbides, you have a better machinability. That is one thing. Second thing, if you improve on your inoculation, you will have a more uniform graphite flake, thin flakes. So when you have a uniform graphite flake, you get a better machinability. When you have a thin flake, you get a more uniform mechanical properties, that is the tensile strength and the hardness. Suppose if you have carbides, your hardness will be much higher. You have a much higher BHF. And if you have a very thick graphite flake, like one of the gentlemen talked about type C graphite, so when you have a lot of type C graphite, or when you have a lot of coarse graphite, you have poor hardness. So in both cases, it is not advantageous. We don't want the hardness to be too high or too less, and that is why an inoculant which a good graphite flake precipitation would ensure that you have the desired hardness, you have the desired machinability in your gray iron casting. How would I know that I need preconditioning? Typically silicon carbide, which amount? You would need preconditioning when your inoculation is good, but you are not getting a good casting. So if your addition rate of inoculant, grade of inoculant, and your ferrosilicon magnesium treatment, if you're doing ductile iron, is okay, and still you're facing problems in the casting, it means something is wrong with your base metal. Typically saying, if you want to achieve 100, you can get 20 from your inoculant, but then your base should be at 80. So if your base is at 70, with the inoculant you only reach up to 90, you still not reach 100. So that's the basic concept of preconditioning. You want your base iron to be good enough for the inoculant to take effect. Now, when you ask typically silicon carbide does have a preconditioning effect, but I would have my doubts on silicon carbide, because prolonged addition of silicon carbide give you much critical inclusion defect in the casting. So silicon carbide is not something which we suggest as a preconditioning effect, because it has got negative impacts. And then you do need to add higher amount of that. Compared to that, a regular preconditioner, like I mentioned about the zirconium and aluminum, we call it pre-seed in Elkem. It has a general addition rate of something between 0.1 to 0.2. You can start with 0.2, and eventually when your system gets richer, you bring it down to 0.15 and eventually to 0.1. How porosity will affect in compacted graphite by changing inoculant, and there is better inoculation in CG iron. Inoculation as such in CG iron is not something which you need to do in a very high rate or in a very high potency. So most common CGI inoculants are the calcium grades and the barium grades. You actually do not need too high inoculation. If you have a porosity defect, the way to solve porosity defect in a compacted graphite casting is by improving on the metal chemistry and improving on your magnesium treatment, or the treatment that you're doing to achieve compacted graphite. It's more to do with your magnesium treatment than to do with your inoculation in case of a CG iron. Is there any study made on the effect of boron and machinability? Yes, we do have it. Boron does have an impact, but boron also has an impact on the graphite morphology. So it's more so the graphite morphology which inversely affects the machinability of the casting. What is the reason for compact graphite in micro and ductile iron under riser? The compacted graphite under riser is because you have a very hot zone under the riser. Your magnesium has stopped making the desired effect. Magnesium, which gives you nodularity, when it fades and when you do not have enough nucleating sites, and when you have a hot zone, it kind of disturbs the nodularity, and that is why you have more of a compacted or a distorted graphite nodule under the riser. Can we eliminate pig iron by adding preconditioners? I mean, basically, pig iron and preconditioners are both added for the same purpose. So definitely, if you are able to introduce preconditioners in your system, we will be able to reduce the pig iron addition to an extent that we can also eliminate pig iron addition. But then again, it depends between foundry to foundry. If I promise you that any foundry can remove pig iron by adding preconditioners, I will be promising you too much. So maybe we'll have to see about the particular foundry and see if we can completely eliminate it. But yes, it can be done. To
Mr.
add
Kislay, I
to
think the questions are popping up. Your topic is very
yeah.
interesting. Maybe we'll maybe the whatever we could see the screen, we will close. I think that questions. Huh?
Okay, so we take these two last questions and close it.
Yeah. That would
Perfect.
be better. Yeah.
Yeah. Currently, we face an issue in gray iron thin wall casting, which is increasing hardness and poor machinability without any changes in charge mix and chemistry. And we use barium-based inoculant in ladle and metal stream. Trapping temperature is above 15-20 degrees. Could you suggest a solution? So, I mean, unless I actually understand your particular foundry to give you a solution off the cuff, it will not be fair. I mean, we can do a lot of things. We can definitely look at a better inoculant or a better process. I don't just go by giving you a better inoculant and solving the problem for you. I would love to, understand the process better. We can connect offline and then I would give you a solution. If inoculant is a solution, definitely that. But when we are talking about this and I just give you an inoculant, it will be like I want to sell my inoculant. That is not the purpose. If I want to solve your problem, I have to understand it a bit better. But yes, we can always change the inoculant and go for a more potent one.
Mr. Kislay, I think there
What
is one
is
question
better
missed out from
inoculation?
Ganapati Subramaniam sir, Breaks India. I think he's repeating the
Yeah.
question, the last one. Yeah.
To address the Boone effect, is there any inoculant developed? You mean the boron effect, I believe, not
Yes,
the Boone.
boron.
Yeah,
Boron.
sorry. Yeah, so we can. I mean, if you have a very high boron, it is going to affect on the ferrite formation, and that is another that is a problem that we have. Better way to do. I mean, you can definitely promote it by having a alinoc kind of an inoculant, which will give you a better ferrite formation tendency. But I would still suggest controlling boron would be a much better way of doing it, sir. It's not a direct impact that we keep on. We cannot add boron and then compensate it by an inoculant. It will be great if we can control boron, but we can try out by having a ferrite promoting element to see if it helps us in mitigating the effect of boron. That can be tried out.
It's like an answer that Venkateswaran's query.
Yeah, Mr. Venkateswaran has asked what is better inoculant for gas defect. See, if it is a nitrogen gas defect, nitrogen Fischer kind of a defect, zirconium-based inoculant does help you solve it. Other than that, control on gas forming factors itself is the way to go, sir. Instead of creating gas and then expecting inoculant to solve it. How to eliminate ingot shrinkage? Let us take it at the last question, sir. Senthil Kumar, sir.
Yeah, I think yes.
How to eliminate the ingot shrinkage in the ductile iron? By having a better nucleating potential with your base metal, and also try and look at your solidification behavior. Maybe the simulation behavior of your casting design, the methoding design, basically. That can be done. But if it is marginal, definitely ingot shrinkage, depending upon the extent. If it is less, you can always improve on the nucleating potential. Use a rare earth based inoculant, and that can help you definitely reduce the shrinkage.
Yes, sir. I think we can close. I think the questions are.
Yeah.
Okay. Thanks, Mr. Kislay. I think thanks for all the participants. I think it's a overwhelming response. I think it is not the participants we could see not only from Chennai chapter across the nation that many people have joined, and I could see a lot of people join from their training room, and many participants have participated. I'm sure the Kislay, the way he has taken the session is tremendous, and in the way the layman can understand, start from what is inoculation, how it functions, what type of inoculation, their importance. It's a classical session for everyone. I'm sure that every foundryman who have participated would have taken a lot of takeaways. And from Chennai chapter, and we thank you very much, and we conduct our regular programs, and we decided to put our webinars across the nation, not only for Chennai chapter, and we also try to put this information in our YouTube channel, Chennai chapter YouTube channel. We will try to share the channel details through our groups. Maybe you can follow later, and then you can also, I also request you to subscribe the channel so that you can get this information at a later stage. And thank you very much, Mr. Kislay, and thanks for all the participants. Thank you very much for a valuable time. Thank you. Thanks for welcome as a group. Thank you.